I'm Leander.
I'm Kirthika.
Myself, Josphine.
We are final year BTech aeronautical students studying in Tech Dr. RR and Dr. SR Technical University, Chennai.
We are going to present you a project carried out by our team in Hindustan Aeronautics Limited, Bangalore.
Our project topic is
Interchangeability of doors and panels on LCA wing nose box assembly, Part B. The second half of the project, our internal guide Mr. Sivaraj, Assistant Professor, School of Mechanical Engineering, and external guide Mr. Dhanaprakash Madam, DM, Assembly Department, LCA Assembly, LCA PG, HAL, Bangalore.
Our project aims at achieving interchangeability by studying the present assembly tooling methods and arriving at the best possible way of achieving it.
As given in the abstract.
Our project aims at achieving interchangeability of the panels and covers located in the LCA wing nosebox region. The first phase of our project is to understand the basic terminologies involved in the project. The second phase deals with familiarization of the technology involved in the assembly process. The third phase involves the understanding of the issue and arriving at best possible solution. In the end, the problem was analyzed in detail and solutions were arrived. The technology requires improvement both in component-wise and in assembly-wise. In this presentation, we are going to see about HAL, LCA, nosebox and its components, the problem definitions and its analysis, concept of interchangeability, concept of tooling, the ways to achieve interchangeability and our proposed way of fabrication to achieve interchangeability, the design process of sub-assembly jig, and finally the 3D layout of jig and its benefits.
The company where we carried out our project is a dream come true for any aeronautical student. Here are the highlights of HAL.
Hindustan Aeronautics Limited came into existence on 1st of October 1964 by the pioneering efforts of late Sir Seth Walchand Hirachand. The company was formed by the merger of Hindustan Aircraft Limited with Aeronautics India Limited, an aircraft manufacturing depot, Kanpur. Government of India became a shareholder in 1941 and took over the management in 1942. Their vision is to become a significant global player in the aerospace industry, and their mission is to achieve self-reliance in design, development, manufacture, diversifying into related areas for global competitiveness and growth in exports. HAL is chairmaned by Sri R.K. Tyagi, and the respected directors of various divisions and complexes are shown in the slide, with their part-time directors, some of whom are respected dignitaries of Ministry of Defence, Government of India. Hindustan Aeronautics Limited has achieved sales turnover of Rs 14,204 crores during the financial year of 2011-2012. The profit of the company soared to Rs 3,329 crores. Its highlights are as shown in the table with the percentage growth over previous year. The products of HAL are very diverse, diversifying into fighter aircraft, helicopters, engines, gliders, light trainer aircraft, transport and passenger aircraft, and unmanned aerial vehicles, most of which are licensed productions and the remaining are indigenously developed ones.
We were so excited to have this opportunity to see and feel India's latest generation fighter aircraft. In fact, our project is going to be implemented in the future production. A little bit more on LCA.
Stages. The LCA program was intended to further expand and advance India's indigenous aerospace capabilities. In the early 80s, it was realized that no organization existed which had the total capability to develop such an aircraft all on its own. The Government of India in 1984 decided to establish the Aeronautical Development Agency to manage the LCA program. Hindustan Aeronautics Limited was to be the principal partner with participation of various respected public and private sector industries. This is the pictorial representation of Tejas in rear view. The multicolored region in the leading edge of the wing is the nosebox region. Phase 1 of the Tejas development is Technology Demonstration Stage or TD. The focus in this phase is on proof of concept. Phase 2 of Tejas development is Additional Testing Phase. This phase consisted of additional testing and development of system using prototype vehicle or PV. Planned production variants are Tejas Trainer, Tejas Navy series production. Future development is Tejas Mark II, featuring more powerful GE F414 engine. The table depicts the physical specification of Tejas. Tejas incorporates a highly reliable quadruplex digital fly-by-wire flight control system. The new generation multifunction displays, head-up display, efficient human-machine interface, and an open architecture computer. Tejas uses GE F404 engine which provides a thrust of 9,163 kg. In the air-to-air and air-to-surface arena, Tejas carries beyond visual range weapons with unparalleled accuracy, giving it multi-role capability.
Coming to our project is focused on nosebox region of the wing. Now see in detail about nosebox and its components.
Nosebox is the assembly present in the leading edge of the wing that houses the front spar, slats, tracks, channels, carriage ribs with roller assembly and actuators. Nosebox jig is specifically designed for the final assembly of nosebox components with front and back panels. Nosebox assembly contains 6 tracks made of aluminum alloy for installing rollers which facilitate the movement of the slats. Given here is the pictorial representation of the LCA delta wing. The multicolored highlighted region is the nosebox, whereas the green colored region is the wet wing which houses the fuel tank. The rear view of nosebox assembly depicts the bottom panels, channels, ribs, stringers, carriage ribs with tooling holes. The top view shows the nosebox with the bottom doors and panel assembly. The bottom view shows the entire nosebox assembly in the rear view.
The problem involved in our project is divided into detailed part study, assembly part study, and 3D modeling as shown.
The problem which our project revolves around is the NB panel's interchangeability. For solving the problem, it is broken down into Cat-A modeling and detailed part study and tooling study. Feasibility study of the located design is carried out for tooling hole identification on the panels. Drill templates and drill jig is designed. Later, it is then fabricated. The fabricated jig is set up and is calibrated. Inspection is carried out before proving and certifying. During the course of inspection, if the jig is found to be faulty, it is then calibrated again. The different ways to achieve interchangeability are to carry out doors and panel assembly on the existing nosebox sub-assembly jig, to modify the existing nosebox sub-assembly jig so that the bottom panels can be drilled and assembled, to provide a separate jig for carrying out bottom panels and doors assembly, to provide sub-assembly jig for each door and panel assembly. Our proposed way of fabrication to achieve interchangeability includes pilot hole being introduced in the NCB itself, drilling of pilot holes using a drill template, but this method requires detailed components and models with pilot holes from design. Drill template required for drilling of pilot holes. The report of the analysis of the problem is given as in nosebox. The assembly of doors and panels are positioned on channels and spice plates These parts are assembled by layout method without any tooling hole or the jig locator or butting plate. Due to this, parts positioning is not consistent. The doors and panels are assembled off jig by Soutron method and hence it is not consistent for every aircraft. Due to the above problems, interchangeability is not achieved. In order to achieve it, every part which affects ICY should have a locating reference for positioning them on assembly, and every doors and panels should be consistent.
We have laid out a systematic plan to carry out our project in series of steps. We have also proposed a way of achieving interchangeability that is as follows.
The sequential planning of our project starts from familiarizing the drawing nomenclature, collecting information on sheet metal process, familiarizing aircraft assembly tooling concepts, studying of the jig design, and laying out of the improvised jig design. Later, modeling it in 3D in CATIA, followed by selection of the material, manufacturing of the prototype design, later compiling of the project report. The basic tooling concept involves positioning of the components on the jig, butting them against the holders and clapping them firmly in place. The tooling concepts involves the concept of 3:2:1 ratio, wherein 1 indicates a point, 2 indicates 2 points between which a line can be drawn, and 3 indicates 3 points between which a plane can be made. For constraining the motion of a part, we need a minimum of 2 locator holes. Now, tooling deals with the design of the locator points for constraining the motion. Interchangeability media is a special category of tools which ensure the proper coordination among the related families of production tools. The types are class MI, MR, TMR, and INM. Class matching interface applies between two components that does not require dressing operations such as cutting, filling, reaming, etc. for matching them. Class matching requirement applies between two components that can be matched but require dressing operations such as cutting, filling, reaming, etc. Class tool matching requirement applies to cases where the assembly tolerance is sufficiently liberal and it is possible to cross match the components. Class interchangeability by nature of manufacture applies to parts that can be controlled during the manufacture process and can be fitted easily to the counterpart of assembly. The given flowchart is our proposed way of achieving interchangeability, in which detailed component model and drawing with the pilot holes is received from the design. It is then given to fabrication of the tool and the design template, also the fabrication of NCB from flat pattern with the tooling lug. Once they are fabricated, they are inspected before the fabrication of the part. Once a part is fabricated, it is later inspected and it moves on to the drilling of pilot holes using the drill templates that is made. Once the drilling of pilot holes is carried out, the holes are again inspected. Later, the part is sent for the finishing process.
For designing any component, the study has to be made. Similarly, the designing of jig following study has to be made.
A complex engineering product is usually designed in progressive stages. An aircraft design goes through at least 4 stages such as concept design, feasibility study, project definition, and detailed design. It is adequate to adapt 2 stages for the design of aircraft's assembly jig, such as preliminary design and detailed design. The picture shown here is a 3D model of subassembly jig with an assembled bottom panel. This jig is our proposed method of achieving interchangeability wherein a portion of the nosebox assembly can be assembled separately before being moved on for the final assembly in the nosebox assembly jig.
In the end, the study of detail and assembly process has been carried out, a nosebox sub-assembly jig has been modeled, and most importantly, interchangeability is achieved.
Finally, study of the detail and assembly process has been carried out. Nosebox sub-assembly chick was modeled using available drawings and is ready to use at any point of time. Interchangeability of panels can be achieved by drilling pilot hole on component stage and using pilot hole as locating hole. Using sub-assembly jig for doors and panels and drill templates for drilling fastener holes on substructure. Thus, by achieving interchangeability in doors and panels of the nosebox area, the overall servicing time is reduced and maintenance is made easier as per customer requirement. The picture seen here is the 3D model of the entire nosebox jig with the portion of nosebox structure that has been assembled in the nosebox sub-assembly jig. The above view gives close-up of the nosebox substructure in its final assembly. The below view shows the isometric view of the entire jig. Thus, layout method and switch-on assembly carried out on nosebox area can be eliminated, increasing the quality of the product. By adopting this method, the doors and panel assembly work carried out as an object activity is eliminated. This method considerably reduces the assembly lead time. The overall project work done may be implemented in the future production of LCA Tejas. This method makes the doors and panels readily available for the LCA nosebox area.
We thank you for your patience hearing of our project presentation.
Soar high into the sky.